start recording our lecture, because like every day I'm going to record these as well as Zoomcast them for those of you that are at home for whatever reason. And then I went and took a quick look at the syllabus turn-ins, and it looked like a couple of people still missed that deadline on Sunday. Not a big deal. Like, I get that it was a quick turnaround on that. I'll extend it out a couple of days. So if you're somebody that missed doing the syllabus turn-in because you forgot or you had some trouble or whatever, try to get that done tonight. So if you were that person that forgot to get their syllabus turned in onto the the PowerSchool Dropbox, see if you can take care of that tonight and get it done. There weren't a lot of you, so there's just a couple of people, but you know, it's the first thing to do the year, and it's not a big deal if you had some trouble or you forgot or whatever. It's not a real assignment, you know, it's just like a thing to practice using the Dropbox to make sure we're all familiar doing that. Okay, so let's start talking about trigonometry. Well, not really trigonometry, but mathematics. We don't start trigonometry in the first chapter, actually. So again, I'm going to do all the notes here on OneNote. They're all saved for you in the content library. If you want to just sit and listen, that's perfectly fine. If you want to write stuff down, that's cool too. If you want to write stuff on your own tablet or you want to write it on a notebook, either is fine. Like it, you know, like I'm not going to micromanage how you're doing your notes or how you're kind of paying attention in class, presuming that you are like, you know, paying attention and engaged and all that kind of thing. Okay? So just letting you know that whatever you want to do, we're going to be starting here in a moment. So if you need to take stuff out, you can take stuff out. If you are just going to sit and listen and do some participating, that's cool too. You don't actually have to take anything out if that's your plan. Again, all of my notes are there for you. The video or the lessons being recorded. So if you're like, that's good enough for me, I'm cool, you can be cool and just kind of sit and participate and listen. If that works for you, that's fine with me. Or if you want to try that and maybe decide later that doesn't work for you, you know, or try taking notes and decide that that doesn't work for you, you know, like you're entitled to change whenever you feel like it. So just to kind of let you guys know, if you look at the content line, notes that we're going to do today are going to be based out of the lessons that are in the content library. So basically what I'm going to do is I'm just going to end up kind of talking through and explaining the ideas and some of the examples that are contained in these lessons. I may do some more, or a little bit more, a little bit less than what's here, but the lessons kind of, you know, are basically the same thing as what the notes are going to be doing. Again, so that's there for you. But basically all I'm doing is like a conversational version of the lesson. Okay? So those are there also in the content library that you can download and alter. Or you could go to the PowerSchool, to the book, you know, to the online book and pull out whatever you need. The whole online book for the year is there in PowerSchool. I'll just, in the content library, throw up whatever the most recent thing we're working on is. So it's kind of got like some kind of organizational to it. Anyways, continuing. Today, we're going to start talking about the first chapter, which is about functions and graphs. So no trigonometry here in the first chapter, just kind of an overview of mostly ideas from your Algebra 3-4 class. We'll probably broach into maybe some stuff that you didn't do exactly in Algebra 3-4. But a lot of these ideas are going to be repeats of things that you did probably at the beginning of your Algebra 3-4 class last year, which is fine. Good to review these ideas because they are important ideas. So the first section is specifically on functions. And so let's just start with a definition of what we mean by function. Does anybody remember what a function is from your Algebra 3-4 class last year? Yes, go ahead. Great. So that's a reasonable definition that you'd give after a year away from the class, and really a good working definition for what a function is. We'll be a little bit more explicit when we write it down because we want to talk about what x and y are specifically. But yeah, that's reasonable and a good functional definition for what a function is. So we'll say a function from the set D to the set R is a assignment, an assignment such that every element in D is assigned to exactly one element in R. Now these two sets D and R, I chose D and R for specific reasons. This set D has a special name. What do we call D? The domain. So we say the set of all input values is called the domain. That's D. And then what do we call R then? The range. Good. And the range is the set of all output values. So you notice that, let's see, was it Jessica that gave me my definition? Okay, Jessica gave us a perfectly reasonable working definition. You'll notice that what I wrote down here is much more precise. Often in mathematics, there's two ways to kind of think about these things that we're defining. There's the working definition, which you'll use to actually kind of think about and conceptualize things. But you really also need a very precise definition if you're going to end up trying to prove anything. So if we're going to try to prove anything, precise definitions are really important because you need to be able to just say exactly what something is and translate what a definition really means and why you can say that based on a definition. But when it comes to just kind of thinking about things in our head and kind of doing a problem and understanding what Jessica did with her definition and just giving us a really easy to understand conceptual definition is also important. So I just wanted to kind of reiterate why I went and wrote down such a seemingly much more technical definition that's really saying the same thing as her, 8-word definition, and why we bother having these really technical, precise definitions is because it makes proving things really kind of possible. Okay, so let's look at some examples of things that are functions or not. So one kind of conceptual way to describe well, let's say a relation. Remember that a relation is the generic term for something that's, an assignment between two sets that may be a function or may not be a function, right? You guys remember that term? So this representation of a relation is called a mapping diagram. And it visually shows how the elements in one set are paired to the elements in another set. So does this relation represent a function? Yes. right? There are two things we need to check. The first thing we need to check is to make sure all the inputs are used, which they are, right? Everybody agree with that? Because they all have an arrow coming out of them. And then we need to check that all of the outputs have only one, or I'm sorry, we don't care about the outputs at all. So we have to care about if the inputs are used, all used, and we have to make sure that each individual input has only one arrow going from it, right? Everybody agree with that? The reason we care about that is a function is useful to us because it's well defined, right? If a function had one input had two different possible outputs, how would we know what answer we want? If I did f of 1, and that could be 7 or it could be 10, how am I supposed to know which one it would be? It's not really clear, right? The reason functions are important to us in mathematics is because it's crystal clear. If I have this input, I must have this specific output, right? There's no ambiguity there. Okay, let's do another example. Does this guy represent a function? No, why not? Perfect, yeah. So between the two of you both said the same thing. So the issue here is that not every element in the domain was used, right? We have x3 that's hanging out. Now, one common thing that we've done in our Algebra 3-4 class, when we had a situation like this, what did we do? We just restricted the domain to be the things that have defined values, right? When you dealt with rational functions, for example, some rational functions have values for x in which they're not defined, right? So what did you say the domain was? Everything except for those values that it's undefined for, right? Remember that, where you have the vertical asymptote? And you can do the similar thing with the range, right? We just say the domain is this restriction, this restricted set, and the range is this restricted set. We just throw out the stuff that isn't defined or isn't used. And now we have a function, right? Okay, let's look at one more example, and then we'll move forward. Is this a function? I heard some yeses and some nos. Take a second and look at it again and think about it. Is this a function? Yes. Okay. Again, remember, when we're looking at a function, all we care about is the domain side. We see that every domain is used, and every domain is used just one time. That is a function, right? Did it matter that this y was used more than once? No. Did it matter that this y wasn't used at all? No. We do have separate names when all the y's are used exactly once. We say that that function is 1-to-1. And when all the y's are used, we say that it's onto. So if the y's are used just one time, it's 1-to-1. If all the y's are used, it's onto. And if a function is both 1-to-1 and onto, that's a special thing. Do you remember those words from your Algebra 3-4 class? Did you talk about those? 1-to-1 and onto? You may have or you may not have. I don't know. No? Sounds like no? Okay. Well, that's okay. We will, I mean, you really didn't talk about, you talked about inverses though, right? Okay. So you probably should have talked about one-to-one at least when you talked about inverses. Because how do you tell if an inverse is a function? Or if a function's inverse will be a function? You do that horizontal line test, which is checking to see if it's one-to-one, right? All one-to-one functions, their inverses are also functions. And that's basic, the one-to-one test. A horizontal line is basically checking to see if a y value is used more than once, right? So maybe in a way you talked about at least one-to-one and you maybe didn't realize it at the time. That's okay. All right. So one representation we have for a function or a relation is this mapping diagram that we've just looked at. Another representation could be with an equation, right? Or a formula. Okay. So question, or another way to describe a function or relation is with an equation like this. So let's look at an example. Does y equals x squared define y as a function of x? So first thing we should think about, can I plug any x into this equation and get an answer? Yes, right? Any number you pick for x, you can plug in there and you'll get an answer for y. Everybody agree with that? Okay. Second thing we should think about, is there anything I can plug in for x that gives me more than one answer for y? No, right? That doesn't make sense. I only get one result, right? Everybody agree with that? So is this a function? Yes. Now, if we rephrase this and said, does y equals x squared define x as a function of y, that's a horse of a different color. Why is that an issue? So let's say we picked y to equal 3. Right? So just an answer. So this is what we have then, right? What values of x would I get? Yeah. So when I square root both sides, I get plus or minus 1. So what are we seeing here? One input gives us 2 outputs. Is that a function? No. So it definitely depends on kind of what we're treating as the independent versus dependent variables, right? In general, this sort of situation is easy to tell right from jump, because if I solve this equation for y, I'm going to get a plus or minus when I do that. Or I'm sorry, solve for x. So I get x equals plus or minus the square root minus 2. And whenever you get a plus or minus going on, when you've done your rearranging to get the independent variable, or the independent variable, the dependent variable by itself, that's going to be an indicator that it's not a function. Everybody's okay with that idea? Cool. So another representation we can have for a function is with a graph. Should probably put arrows at the end of these. Do you remember the easy way to check if the graph of a function, or I'm sorry, if a graph represents a function or not? Yes, sir. Great. What kind of line? Vertical line, yeah. So we'll use I like to abbreviate that just as VLT for vertical line test. And what that says is that the VLT defines y as a function of x if and only if. So the IFF like that is just an abbreviation for if and only if. Remember that if and only if statements can be read forwards and backwards, right? There is no vertical line that intersects the graph more than once. So let's just letter those graphs there in this example. So graph A, is this a function? Yes, right? No matter how we draw that vertical line, it can only intersect that graph at most one time. Everybody agree with that? Okay. So that's a function. How about graph B?
Please excuse this quick interruption. If you have not had your picture taken, for your ID, please get to the media center right now. Those students that have not had their picture taken for their ID yet, please get to the media center to get that taken care of with your form. Faculty and staff, we'll keep that open until 3 for you, but make sure you get that done before the end of today. Thank you.
So yes, B is a function. Again, no matter where we draw that vertical line, we're only intersecting the graph once. How about this last one? No, right? This is not a function. Does it matter that I can draw a vertical line that doesn't intersect the graph at all? Does it matter I can draw a vertical line that intersects it exactly once? No. All that matters is that there are vertical lines I can draw that intersect it more than once. So even if I went back to, say, graph A, and I said, oh, the graph is this U and this extra point right here, that would all of a sudden not be a function, right? Because there's a spot, specifically this line here, that you could draw that intersect the graph more than once. That's assuming we added in that one extra point, right? Does everybody see that? Okay. I'm just going to back those off so that when you look at the notes in the future, you weren't confused. Okay. The last thing here is we want to talk about in this first section is called function notation. And the way function notation looks like is we start with like f of x equals. Hopefully you guys remember this from your algebra class last year, right? Where the x is our independent variable and the f of x is the dependent variable. So basically what we're saying is that if you had y equals 3x plus 4, that's the same as like f of x equals 3x plus 4, right? The benefit of using a function notation rather than the y equals notation is if I want to talk about what the y coordinate is when we plug 5 in for x, we don't need to use a bunch of fancy language to do that. We can just write like f of 5. So that's talking about the y coordinate when x is 5. Everybody's okay with that idea? Okay. Guess what? That was section 1, all done. Whoa! We're just ripping and rolling here, folks. It helps that this is all reviewed, though, right? If this was brand new things, I would not be going this fast. Or maybe I would if it was really easy, but, you know, probably not. Okay. Domains and ranges. Again, my expectation is hopefully that you spent a little bit of time last semester talking about domains and ranges, or a lot of time, depending on how you classify a lot versus a little. So, quick question for you guys. When you talked about domains and ranges last year, what form did you write your domains and ranges in? Did you use interval notation? Okay, for the most part, good. That's what we'll prefer to use here. So let's just write a couple of inequalities and translate those into interval notations. So let's say we have the inequality x is less than or equal to 2. So the first thing I like to do is I like to think about what are the bounds for this inequality. So what's the smallest number that's less than or equal to 2? The smallest number less than or equal to 2. Negative infinity, right? So there is no smallest number. You can keep going on forever. So the symbol we use to represent that is negative infinity. What's the biggest number that's less than or equal to 2? 2. Okay? Now we have to decide whether each end of this gets a parentheses or a bracket. With the infinities, we know that we always use the parentheses. And then to decide whether I should use a bracket or a parenthesis for a number, I have to look at the inequality symbol. If it's a strict inequality, we use the parenthesis. If it's an or equal to inequality, we do the bracket. So in this case, we use the bracket. Any questions on what we did there? Okay. And I guess really if we're going to be specific here, which we probably should be, notice how in part A, the variable is x. So probably I should say x is a member of that interval. Because in part B, I use a different variable, right? In part B, I'm using y. So let's just start off with the y is a member of, and then we'll write the interval. Since we're going to be talking about domains and ranges, it's important to differentiate whether we're talking about the set of x's or the set of y's. So we're going to be specific here and use that little notation to indicate whether we're talking about a domain or a range. Is everybody okay with that? And that little symbol's like a curvy E. It's just the symbol that means is a member of. Because an interval is just really a set of numbers, right? Okay. So -5 is less than y, which is less than or equal to 10. What's the lower bound? -5. And the upper bound? 10. The -5 should get a parenthesis, and the 10 should get? Good job. Let's do a sneaky one here. So we know we're going to have A as a member of. Now, how do we deal with this OR part? Do you remember what to do with that? You're going to use two sets of parentheses, good, or brackets, depending on what you want to use. And what symbol is going to connect them? The U. This stands for union. And that's basically the set version of the word OR. So A is a member of this interval, or it's a member of this interval. That's what the big U there means. And we don't put a tail on the U's, just FYI. It's like a cup rather than a U. But anyways, all right, so let's look at the first inequality. The lower bound is -infinity, and the upper bound is -2. The -infinity gets a, the -2 gets a. Very good. A is greater than or equal to 5. The lower bound is 5. And the upper bound? Positive infinity. Very good. The 5 gets a bracket, and the parenthesis gets, the infinity gets the parenthesis. Yeah. Is everybody okay there? So again, no big deal. You just have to remember that union symbol goes in between. You just treat the two inequality as two separate intervals. Not too bad. Okay with that? Okay. What we're going to do now is we're going to define something called the implied domain. And this is related to this example here. When I talked about, hey, we could make this a function by just excluding x3 from the domain, by restricting that domain down to just being the stuff that creates a function. That's kind of the idea here with an implied domain, is we're just going to kind of imply that we're doing that. Or it's implied that we're doing something like that. Okay. The implied domain is the set of numbers that are algebraically possible from the given function. And that result then gives a as the set of numbers that logically fit based on the situation. And now this seems kind of vague and maybe not that clear. Oh, I'm sorry. This isn't range. This is relevant domain. So we have an implied domain and the relevant domain. Excuse me. So it's worth noting that the relevant will always be a subset of the implied domain. What do I mean by a subset? I mean everything in the relevant domain is in the implied domain, but there could be things in the implied domain that aren't in the relevant domain. Okay, so the relevant domain is always the smaller of the two. Well, I shouldn't say small. It cannot be the biggest. They could be the same size. That's okay. And we'll do some examples here to clarify this, because as tricky as this sounds, it's really not very tricky. Okay? Okay, so let's look at this. In this situation, in an algebra class, what set of numbers is it generally accepted that we're working from? The real numbers, right? That you can have decimals, any kind of decimal would be okay. Everybody's okay with that idea? That is our implied domain in this problem. So let's use a red. In general, anything like this, where you have f of x and x, the implied domain is the real numbers. Now, can I plug any real number in for x and get a real number result to this function? What do you guys think? No, right? What's the problem? Yeah, it's possible, depending on what value of x you pick, that you might be square rooting a negative. Everybody agree with that? And that's a problem because that doesn't result in a real number. So our implied domain is all real numbers. Our relevant domain, we know that the part underneath the square root has to be bigger than or equal to 0, right? Because if it was less than 0, you'd have a negative number, and you can't take the square root of a negative and get a real result. Everybody's good with that idea? So I just add 4 to both sides, and I get that x has to be greater than or equal to 4. So when I convert that into an interval notation, I get that my relevant domain is bracket 4 to positive infinity. Is everybody okay with that? And it should be clear by looking at this that 4 to positive infinity is definitely a subset of all real numbers, right? That's just part of the number line. Let's do another example. So again, this is just like a g of x and x. There's nothing specific about this. We can just, the implication is we're dealing with the real numbers, right? Yes? We're going to see an example where it's not here in just a second. But usually some context needs to be applied to the question in order to get that. You'll see that here in the next example. But Delaney, I would say that whenever you're given just like this with no context applied to it, yes. Like if you just have like function notation equals algebraic expression with nothing else, then yeah, the implied domain would be all real numbers. Okay, so what kind of a function are we looking at here? This has a name, right? We talked about it last year. Starts with an R. A rational function. Where do we get in trouble with rational functions? When the denominator is 0. So, what do we care about? Is simply when the denominator is not 0. That's going to give us our relevant domain. So I get that x cannot equal -2. But that's not entirely clear how we'd write an interval from that. Can we take x cannot equal -2 and rewrite that as a pair of inequalities? Yeah, right? This is the same thing as saying x is less than -2 or x is greater than -2. It just can't be -2. Everybody's good with that? So now it's easy to write our relevant domain because we've translated this into inequalities. So we have -infinity to -2 union -2 infinity. We okay there? So whenever you're dealing with these rational functions, you'll almost always have a union involved like that, because there's usually one half of it before the vertical asymptote, and then one half after the vertical asymptote. And if you have more than one vertical asymptote, you're going to have, possibly more than one union, right? Everybody's okay with that idea? Okay. Good. Our last one maybe I shouldn't say side. Maybe I should say edge, since we're talking about a cube. Okay, the last one, v of s is equal to s cubed, where v of s is the volume of a cube with edge length s. So here, the implied domain is different. Why? Perfect, because S, the independent variable, is talking about a length. A length cannot be negative, right? Really, can a length be 0? I would say that a 0-length cube is not actually a cube, right? If the side lengths are all 0, what the heck is that? It's a singleton point and not a cube anymore. So really, I would say that our domain then, our implied domain, is this. Since we have some real-world context attached to it, lengths we know cannot be negative or 0, at least for a shape. So that implies that our domain is dealing with only positive values. Is everybody okay with how I read that from the question? And you see that to get an implied domain that was not all real numbers, we needed some context attached to some real-world context attached to the x's and y's, right? Or in this case, the v of s's and s's. Now, of the things in the implied domain, can I plug all of those in for s and get a value to return? Do all of those values make sense as values for a volume? Yeah, since they're all, if I plug in a positive number into this function, I'm going to get a positive number result back, right? Everybody agree with that? And that's what I should be getting for a volume, right? So nothing seems like it's a miss. The relevant domain is the same as the implied domain, which we said could happen, right? Just that the relevant domain can't be bigger. Everybody's okay with that? Okay. So let's talk here about ranges. Now, ranges are typically trickier than domains, right? Because the range is based on the domain. So one way, or probably the easiest way to approach this, is just kind of using our calculator, our graphing calculator, to look at the graph. Everybody's okay with this plan? So if you have your graphing calculator and you want to follow along, you're welcome to do that. If you're just like, I know how to graph things on my calculator, that's not a big deal for me. You can just kind of sit and watch, because that's all I'm really going to be doing with it, is just graphing these functions. If it'll open, which it seems like it's being really slow about. Maybe I won't get a chance to do that. Yoo-hoo. Maybe it's thinking about it there.